In a graph neural net, we are moving from arrays to points of data in spatial relation, or nodes, and their relationships, or the lines between, or links. In doing so, we can use the relative position of nearby points to provide information about the structure or patterns within, and predict relationships or classify the nodes or the entire structure itself. When applied to the real world, the benefits are massive. Now, this should sound familiar, as we've previously discussed nearest neighbors as a method to provide, surface, and extract data from abstractions. These neural nets are used in recommender systems, science and medical research, cybersecurity, data analysis, transformation tech like new materials design, etc., etc., etc. So they have lots of uses. So these elements are the foundation of graph neural networks, and you should see something familiar from the prior sections. Graphing neural networks surface information from nearby data relevance. Chat AI responds to an input by interpreting words in relation to their neighbor words. Very similar type of methodologies. ChatGPT also produces a response of words in relation to its quote-unquote neighbors. This whole thing is the foundation of context in both human and artificial intelligence systems. And the human's ability to exhibit lightning-fast response to stimuli. This is what we use to do it. We use this sort of proximity methodology. Now, this has immense value to the future of AI response systems and AI in general, as it gives AI systems spatial self-awareness, both direct, as in autonomous cars, or indirect, as in general AI stimuli response systems. The input layer to a graph neural network is basically the x-y axis of graphs or additional dimensions. These additional dimensions form the foundation of multi-angulation, or the connection to other graphs, or links to other data in other graphs or arrays. Multi-angulation is simply increasing the dimensionality of abstraction and representation we discussed in prior sections. This is not too complex because you use it every day when you link specific things in variant contexts, like a nice sunny day to putting that fence post in, or having a picnic. Both picnic and sunny day have vast context themselves, but are related through a shared context of doing something outside on a nice day. And yet again, we use convolutional layers, which we discussed before, and an additional aggregation layer that is the use of neighboring data for clustering, which yields more data about the nodes and the relationships. Then we have structures we have covered before in other neural net sections, such as activation functions and pooling layers and output layers and optimization methods, so I won't rehash all that stuff. Instead, this is the code of a simple graph neural network. Again, don't focus on the code, because we have coders and dev to do that, unless you're a dev, in which case you need to be in the dev bootcamp. For our purpose, we just want to be familiar with the code structure. And as usual for demo purposes, Python, but you can use any code you prefer. I use Python, and not very well, which is why I have devs and CTOs and math PhDs and other people to do the heavy lifting. Once again, we import the torch library. Then we define a convolution class, and within it you can see we're calling specific functions, mathematical functions, or math library functions. You should always keep in your head that anything you perceive must be converted into something that a machine can perceive, and graphs are just arrays to a machine with some high school math applied to them. That's it. Of interest in this section of code is the use of the adjacency functions. Now, previously we saw k-nearest neighbor functions in a previous section, so again we're using that neighborhood methodology to extract and surface data and relationships. In this case, we're extracting information from co-located matrices and their relationships or links. Then we run the model and puke out an output, in this case the node features of an adjacent matrix. And once again, going all the way back to some of our earlier sections where we discussed all of these features in neural nets. This should all be coming together in your head now. And here's the output at the bottom of the screen. Again, all just run locally on the laptop, and you can all do this easily yourselves. The output in this case, no surprise, is a tensor that we discussed before in the tensor intro. The point of all this is that there are different types of neural networks for different purposes and applications, and in the investment section, you need to know this to comprehend what you are actually investing in. For the rest, you can now at least comprehend what it means when the world discusses advanced AI.